Welcome to the set of lectures on second law of thermodynamics. In the series of lectures, we address the first law of thermodynamics, which is just the statement of conservation of energy in the context of thermodynamics. We moved from conservation of energy in mechanics to conservation of energy in the context of thermodynamics. However, there are a variety of processes that do conserve energy, but that doesn't occur naturally. Okay, so for example, if you have a hot cup of coffee, there is a thermal energy transfer, heat transfer from cup of coffee to the atmosphere, surrounding atmosphere, till the temperature becomes the same. But the reverse of this process, that is the cup of coffee spontaneously taking heat from the environment and raising its temperature, does not occur. For example, you have a cylinder of air at a higher pressure. When you open the valve, air is released from the cylinder till the pressure in the cylinder is equal to the ambient pressure. But you don't see spontaneously air getting into the cylinder and such that the cylinder pressure increases. If you have, let's say, current flowing through an ohmic resistor and doing electrical work, you release heat. However, if you supply heat to the ohmic resistor, you don't really get electrical work out of this. Okay. A common example, you have a mass that is dropping down. The potential energy is converted to kinetic energy, but you don't see the opposite occurring. Okay, suddenly, all the mass, the exact reverse of this process doesn't occur. We spent quite some time on the Joule's experiment, wherein a mass was lowered and this rotated a shaft, okay, and generated heat. However, when you supply heat to the same system, you don't see the shaft rotating in the opposite direction and raising the mass. Okay, so what is the crux of all these examples? The crux in all these examples is that energy is conserved both in the so-called spontaneous process and the processes occurring in the reverse direction. However, in general, you see the processes tend to occur only in one direction, but not in the opposite direction. Okay, so why is that so? That is the question that second law tends to answer. Okay, so there is a certain directionality in the processes, and second law explains why that is so. But beyond this, the scope of second law is rather wide. It gives you a condition for equilibrium. In the previous example, I said that heat continues to flow from the hot mark to the environment till the temperature of both the system, the cup of coffee and the environment, is one and the same. In the case of air coming out of the cylinder, the pressure happens to be the same, right? So why is this the condition of equilibrium? So in general, we are going to address the condition of thermodynamic equilibrium quantitatively. While there is a flow of heat, for example, from a hot object that is higher in temperature to an object that is lower in temperature, while there is a thermal energy transfer, heat energy transfer, there is always a potential to do work. Okay, so as the system tends to go towards equilibrium, we are trying to understand these kinds of processes. When there is a flow of gas from high temperature, higher pressure to lower pressure, while the system and the environment tends to attain equilibrium, there is a potential to do work. We are trying to understand these kinds of processes. What is the nature of work you can obtain from such fluxes, from such flows? We are also going to differentiate work and heat. Okay, not all both are equivalent from the first law in some way. Both are energy. However, the quality of energy is different. Work is of higher quality compared to heat. All of work can be converted to heat, but all of heat cannot be converted to work. We want to clarify this statement. Why is this so? Okay, so that's one of the central points of second law. And there are, in this case, I said, right, there's a potential to do work. We are going to talk about the efficiency. What is the maximum work that is possible when you convert thermal energy to work? Okay, when there is a flux of thermal energy, how much of it can be converted to work? Some of the processes, for example, in refrigeration, you need to put work into the system. Can I get bounds on the work that is that we have to put? Okay, what is the for in this case, what is the maximum work that you can get? What is the minimum work that you have to put into the system? Okay, so bounds on work generation and work requirements are going to be answered by second law. And second law will help us in defining a temperature scale that is independent of thermometric substances. When we dealt with thermometer, we always dealt with some fluid, okay? So there is in the thermometer. But here we would see that none of that is needed, okay? So we are going to define a thermodynamic scale that is independent of all thermometric substances. This is a very profound thing. And there are going to be very useful ways of how to connect measured quantity to computed properties. Okay, there is going to be a zoo of partial derivatives you will see in time, where we will be connecting all these things, not only in this set of lectures, but in the later, towards the end of the course, also we'll revisit these kinds of topics, how to connect what is being measured to computed, what is being computed. Overall, the scope of second law is rather wide. It's used in communication engineering, storage and transmission of information. It's used in economics. It's used in philosophy, and so on. So it's good to have a feel for the historical context of the second law. So much of the advancement in thermodynamics is on practical need, how to get work out of a system, how to build devices that provides work. Okay, so the tedium of human labor is decreased, and you want to have a device that is able to generate work. James Watt did a lot of this kind of work. The second law, the origins of second law is attributed to Carnot. Okay, so he was a French engineer. All these French engineers were trained in military institutions. Okay, the military institution wanted to train engineers so that they would be useful to the military. It's very interesting. Many profound scientific laws concept came out of these military schools, because the kind of instructors who teach Ampere and so on came out of this military school. In fact, this is the son Carnot. Much of his interest was driven by his father. Okay, so father was also a military person who worked under Napoleon. So he had interest in these kinds of work-generating device. Some of his interests came to the son, and the son developed what is called he developed a pattern, what we refer to as the Carnot efficiency. It's a very nice generalization. Unfortunately, he died very young. As you can see, he died very young, and he published only one scientific work. He used his own money to publish a book that was distributed, but it was not widely popularized at that time. Okay, so his brother actually didn't share his notes, extensive notes with others. It was actually Clapeyron. Okay, so as you can see this photograph, Clapeyron seems to be reading all the time. Okay, he must have been, he came across Carnot's book and he popularized it, and he did also he extended much of the knowledge that is available through the second law. So it's good to have a timeline on which century gave us what. in 1600s and so on, the Newton was there. A lot of mechanics, celestial mechanics was, laws of celestial mechanics was framed. I would say 1700s, especially middle of 1800s was the century of thermodynamics. All right, so a lot of interesting things came out of that. Then Gibbs and Boltzmann also contributed to molecular understanding of thermodynamics. And then there was also electromagnetism, Maxwell. Okay, so electricity and magnetism also was parallelly developing along with thermodynamics, statistical mechanics. So by 1900s, what we call classical physics, classical mechanics, electricity, magnetism, and classical thermodynamics and statistical mechanics was well framed. Okay? So Planck even made a statement saying that almost all of physics is understood. But early 1900s came the revolution of quantum mechanics, what we refer to as modern physics. Okay, so that came later. So this, I won't go through this entire thing. It's good to have a timeline on what are the important development in thermodynamics. I got it from this textbook. And you can see much of this is about devices that generate work. Okay, there is heat engine here, fuel cell, even as late as 1900s, people were interested in making useful devices. Okay, there's Otto cycle engine and so on. You will see all these things in the later part of the class. Okay, so as I said, thermodynamics about energy transformation and about properties, especially course on engineering thermodynamics, we focus a lot more on energy transformation. So in the next lecture, we will look at heat engines and lay foundation for Carnot efficiency.